Okay. بسم الله الرحمن الرحيم الصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone. Today inshallah we're going to be starting with the topic number 3 of the course. So we're done with topic number 1 about the mathematical foundations. We're done with topic number 2 about rigid body dynamics and describing the rigid bodies using elements or Lie group theory. Today inshallah we're going to be moving on to fixed base manipulators, which will be using the tools that we learned so far in describing one rigid body. And now we're going to be connecting several of these rigid bodies together. And the last link, or the first link, will be connected to a fixed base. And we're going to be, again, describing these general purpose manipulators in that sense. You've seen the email about the announcement on the project. So deadline is this week, first milestone, choose team, choose the robot. By email, okay, or by the discussions at any time. You can ask if you have something in mind that you want to work on, whether it fits the scope of the project or not. When was the second milestone? 2 weeks, I think, right? Something like that. So in 2 weeks, you're going to have to describe your robot on paper. We're describing putting the reference frames, describing the links, describing the joints, using the tools we're going to be discussing today. So this is very important for the second milestone. Okay, so after this lecture, this one and the next lecture, you can start working immediately and finish the second milestone. So let's start with motivation. Anyone has a question? Yeah.
So, due to the variation and complexity of
Yes.
they're like rubric, like what exactly? So for some that will come on the next project.
Yes.
System, or there are some constraints they didn't take into consideration, or some things like that. How will that affect their marks?
The project complexity is definitely part of the marks. I think about 5% will account to the project complexity. Okay, so the most complex project will take 5 and start it from there. I will not go to 0, okay? But again, so there will be some distribution among the project, because definitely the people who chose something that's complicated will get more marks because it will be more involved in the documentation and the work and so. Okay. Why is that? No, okay. So in this topic, we're going to be dealing with the kinematic and dynamic modeling of fixed base open chain manipulators. When we say fixed base open chain manipulators, this means we're going to be ruling out manipulators that have closed chains. So for example, a delta robot will not be, we cannot deal it with the tools here. An extension of it, but not directly what we're going to be learning in this topic. And also floating base manipulators, we need something more than just the tools we're going to be describing today, even though a lot of it will be similar. So this will be the last topic of the course, inshallah, the floating base manipulators. But today we're going to be focusing on the fixed base manipulators. These fixed base manipulators, we can think of them as the following: several rigid bodies connected to each other by ideal joints. And when we say an ideal joint, we're going to be spending some time here trying to describe what do we mean by ideal joint, how can we describe it, again, using the Lie algebra approach we discussed, and how can we connect these rigid bodies with these ideal joints together. An ideal joint, another name for it is a kinematic pair, is a purely kinematic relation. So there's no dynamics involved, there is no forces involved or wrenches within these with the definition of these kinematic pairs. And it's simply a kinematic relation that restricts the motion between two rigid bodies. That's it. So if you have two rigid bodies and there's a joint in between, this means that these two rigid bodies, each of them separately had 6 degrees of freedom, but when they are connected together now, they have less than that. Okay? So this is what the ideal joints do. And we can, in terms of what we learned, so the degrees of freedom of a joint are equivalent to the number of independent coordinates that we have in the relative twist between body 1 and body 2. And again, expressed in any frame. The expressing in any frame, you know now, it's again just a way you're an observer, but this like abstract object, V1 with respect to 2, is well defined no matter where you look at it. For example, here are a number of these examples. We said that if you have two rigid bodies moving with respect to each other completely free, then we have 6 degrees of freedom between the pose of body 2 with respect to pose of body 1. And these 6 numbers, we describe them by how many numbers? So this is the 6 degrees of freedom. How many numbers do we describe this relative pose? 16, exactly. So we have a 4x4 matrix. Again, it has a very special structure such that it corresponds to rigid body motion. When we have a revolute joint, the revolute joint allows only rotation about one axis. So the relative twist between these two bodies will have how many degrees of freedom? Only one. So a revolute joint will allow only motion in one direction, and it will restrict the motion in the remaining 5. Okay, so this is why if there is no joint, it has 6 degrees of freedom. When we have a revolute joint, this means we're constrained 5 when we have one left that we can, okay, either freely rotate or with an actuator. The other example is a prismatic joint. The prismatic joint is similar to the revolute joint, but just instead of having something that's rotating, something that is translating. So two rigid bodies relatively moving in one axis compared to each other, translating. And then we have another example is spherical joints or ball joints, for example. They constrain 3 degrees of freedom and they allow 3 degrees of freedom, okay, with respect to the relative twist between these two bodies, 1 and 2. Does anyone know which 3 degrees of freedom are constrained, not allowed to move? The linear ones, exactly. So you have allowed 3 rotations, but not any linear translation. It's not allowed to move in the X or Y or Z in whatever definition you defined. The forward kinematics is the name for which is a map. So the forward kinematics is a map that, and it's also a process of calculating the forward kinematics, the calculation of the position and orientation of the end effector. So usually when we have a fixed base manipulator, the last link or the last point or something, we have a very special end effector or a very special like device put in the end. This is what we call in robotics the end effector, because this is usually what, for example, it's like the camera that's looking at the environment, or this is like the hand that's like the tip of the tool that's doing some operation. So this end effector frame, the map from the joint coordinates to the end effector frame is known as the forward kinematics. And let's take an example. So this is should be trivially, that you can do on paper in like, I think in 5 or 6 minutes. So this is a 3R planar open chain manipulator. So when we say 3R, what does that mean? 3 revolute joints. And it's planar. What does planar mean? Even though it's a number of rigid bodies, but we see it's only moving in one plane. Okay, so it's not allowed to exit this plane at all. Even if theta 1, theta 2, and theta 3 change, it will always remain in this plane. Okay? Even though, just as a side remark, even though we can do SO2 and SE2 stuff, right, and write stuff with the algebras in 2-dimension and so on, it's much like easier to stay with the SO3 and the SE3 stuff that we learned without introducing any more notation or any new like operations, because simply what is the rotation here about which axis? So if this motion, for example, above the end effector in X and Y, okay, is moving in the plane, what about the angle or the angular velocity? In which axis is it? It's in Z, right? So there is no such thing in the end as actually planar motion, because the rotation is always in the third direction. Okay, so that's why for simplicity, you can always work with SE3 and you're going to be losing nothing. Okay, so you no need to define like special notation or special like math for the 2-dimensional case, which exists, by the way. You can find it in some books, SE2 and SO2, but again, we don't need that in our case. The forward kinematics map that goes from theta 1, theta 2, and theta 3 to the end effector position, which in the end here we can represent the pose, the pose here is the 4th frame that we have. So this is the end effector frame, and the pose of this end effector frame is given by this 4x4 matrix. Again, we have here 0, 0, 1, 0, 0, 1, because this is rotation about the z-axis, and we simply have this angle in the end of the end effector is given by this angle phi. And you can check for yourself visually, okay, very easy, that phi is simply given by theta 1 plus theta 2 plus theta 3. The x and the y position are given by simply just, again, the cosine, the projection of these lengths in the x and y direction. Okay, is this trivial for everyone? Everyone is easy? Okay, so open chain versus closed chain. Are you familiar with the 4-bar mechanism? So for example, if we take this last bar and we attach it to the ground also as well, this is a closed chain. If you have a delta manipulator, for example, delta manipulators are known to be very fast. Okay, and this is also like something with closed chain manipulators. They are usually they have a very good dynamic response or dynamic what's the word? Dynamic behavior. But open chain are more again, they are more popular. Again, both are popular. Again, you can find applications where both are available, but we're going to be dealing with the open chain ones. Okay, so this is an open chain. What is the systematic way of doing it? So now you can do this by using trigonometry, and this is where it's easy. But if you make it more complicated, if you take a real robot and try to do the same with basic trigonometry, it won't work. Okay, if you tried before, then you know how difficult this is. And we'd like to have a systematic way of doing that. One way of doing this is simply by attaching a reference frame to each link. Okay, so you look at every link that you have in your robot, and you put on this robot again. We put on this link a body fixed frame. So here, for example, we have body fixed frames 1, 2, 3, and 4. So this is link 1, and frame 1 is attached to it, so it rotates with it. Frame 2 is attached to body 2, and frame 3 is attached to body 3. Okay, so for example, if we fix this part and we have this link alone, it starts to rotate, you're going to find that frame number 3 is rotating with it. Okay, so frame 3, frame 2, and frame 1 are attached, okay, are body fixed to each of these different links. Then simply we have by what we learned about the homogeneous transformations, that if I would like to have the homogeneous transformation or the pose, the relative pose of the end effector frame, frame 4 with respect to frame 0, which is the stationary frame that we have here. Here, just as a small remark, that here frame 0 is at the same point of frame 1. Okay, it's just written like that so that it's clear what that means. Okay, but there's like this arrow that says that frame 0 is at the same point where frame 1 is attached. Frame 1 with respect to 0. So you see, 1 with respect to 0 is a function of this angle theta 1. 2 with respect to 1 is a function of this angle theta 2. 3 with respect to 2 is a function of this angle theta 3. But 4 with respect to 3 is just a constant. So this is just an extra like translation along this link, so that we go from this joint to the end effect. A very famous way of, again, you have a question? And the other side, this one or the one before? Yeah. Again, so x is L1 cosine this angle, L2 cosine this angle and that angle, L3 cosine this angle and this angle and this angle. Okay, then you get this x expression, and then same for the y, but sines instead of cosines. Okay. If we do it like this, and again, consider only the homogeneous transformation that describes the relative pose only between each of these frames in terms of their corresponding angles, and then using some trigonometric identities, we can in the end get the same expression for this. And you can try it out for yourself if you don't believe it. But we're not going to be doing this approach. We're not going to be doing the basic trigonometry. And we're not going to be doing the DH parameters. Who's here familiar with the DH parameters approach? Okay. So if you took any robotics class before, then one famous way of actually placing these frames, again, is trying to choose them in a very smart way such that you make your life easier. This is the only thing. So there's nothing computationally fancy about it other than making, describing these frames on paper become easy. And again, this is where we're going to be parting from the standard way of dealing with homogeneous transformations, and we're going to be working with something known as screw theory. Okay? So there is a screw theory interpretation of twists, and try to describe these relative poses in a very, very fancy way. And again, of course, it has some mathematics behind it. We're going to be trying to explore this today. Okay? So the end result is that what we're going to be doing today is trying to find an extremely systematic way of defining these homogeneous transformations, such that doing it for this example or doing it for something more complicated will become a piece of cake. And again, we're going to be hopefully having some time to go at some examples so that you can try yourself. Okay? So we're going to be starting with a concept of exponential coordinates. Okay, the exponential coordinates and the exponential map are two special structures of the Lie group SO3 and SE3. We're going to express again, try to investigate them more, and then later we're going to be looking at how we can use that to solve the forward kinematics problem. Let's start again, go way back to an old class on ordinary differential equations. So this should be familiar to you. Okay, if not, let me know. So x dot equal to a x of t, again, a linear ordinary differential equation where x is simply a scalar and a is a constant. And the solution to this equation, you should know that it has this exponential expression where x at any time t is given by the exponential of at multiplied by the initial condition that you started with. And you should also be familiar that this exponential is calculated in general by this series expansion. Okay, makes sense to everyone? Can we do the same for matrices? Yes, of course. So if we have a vector linear ODE, x dot equal to a x of t, everything else holds the same, where x of t now lives in Rn, so it's a vector in Rn, and a is a constant matrix. X of t, the solution of this ordinary differential equation, is again the matrix exponential. So e power at is the matrix exponential multiplied by the initial condition x of 0. And this matrix exponential is defined in the same way as an expansion of at in this way. Clear? Okay. Now let's look at a very special equation that we dealt with for a while now, which is this one. R dot is equal to omega tilde multiplied by r. And let's, again, try to look at it from a different perspective. This expression, you know that it describes the instantaneous change of the relative pose of frame B with respect to frame S. And we know that this instantaneous change of the rotation matrix is related to the angular velocity by this weird map that you all know how it looks like by now. The angular velocity vector, which is omega b with respect to s, and when we write it without the third frame, what does that mean? Coordinate free, the abstract vector, right, which is this one, right? So this vector that you see here in the figure, we can represent it as the multiplication of a scalar and the unit vector. Okay? So any vector in R3, you can express it as a unit vector, so something that has magnitude of 1, and the magnitude of that vector, right? So it's like something very trivial to do. This direction, which is the nbs hat, is simply the axis around this rotation, about which this rotation is happening, and theta dot is the angular velocity around which you're rotating. So just to give you a small example, so if I'm rotating this frame like this, where is n hat? Upwards. And let's say, for example, I'm rotating by 2 rad per second. So again, so 4 rad per second, 5 rad per second, and so on. Okay, this is how you can visualize it. If I'm rotating around this axis like this, so I'm rotating like this, and if I'm rotating like that, this axis. But in the end, I can rotate about any general axis, okay, which is what we call here n hat, and I can transform this S frame into the B frame by some sort of rotation. Okay, so this is one way to visualize what the angular velocity is. If we look at the R dot from this perspective, we see that we can think of it in a different way. We're going to assume for a second that we have theta dot equal to 1, which means that the omega is equal to n hat. And n hat is constant. So this is also another assumption. We're going to be assuming it's a constant, so it doesn't change. So I'm rotating only around one axis. It's not this axis is changing. It's only fixed, and I'm rotating around this fixed axis. Which means that this differential equation becomes very similar to what we just saw right now, that we have some sort of x dot, but now it's a matrix. X dot is equal to some constant matrix multiplied by x. But now this x is a matrix, x dot is a matrix, and x is a matrix. Okay? So x dot is equal to ax, and what is the solution of it? That x of t is equal to the matrix exponential of x at time 0. Clear? Okay. Intuitively, what are we? Yeah. Again, this makes sense to you? Okay. So if we change x dot to be a a matrix. Let's call it capital X dot. And this is capital X. So this is n by n, n by n, n by n. Make sense? Okay, what is the solution of it? Similar, x dot, capital X of t is equal to the matrix exponential of at multiplied by capital X of 0, which is also n by n. So n by n, n by n, n by n, and this is the same. So this is precisely what we have, 3 by 3, okay, matrix. Okay, this is the differential equation in a 3 by 3 matrix. But again, the solution is the same way. This is very similar, again, to what we just saw, because we have a linear map. Okay, so this is, again, we're talking about a linear map, so this all makes sense. In general, this is not true. So in this case, if you see here this exponential, this matrix exponential, you can think of it this way, that I'm starting with some sort of initial rotation matrix between B and S at time 0. And then I'm rotating it. Okay, I'm doing some sort of rotation around an axis, which is n hat, for 1 second at a speed of 1 rad per second, and then I reach this rotation matrix. Okay, so I'm gonna describe it, do it visually here. So this is, let's say that this is the axis, it's fixed, and I'm rotating with 1 rad per second in this way. So you see, at every time, I'm getting a new rotation matrix. Okay, I can rotate the other way around, and again, it's the same. Okay, so you all visualize it. So this is what this equation does. Okay, so just a solution for this ordinary differential equation in the case, this is very important, in the case that this unit vector is constant. It's constant, it's not changing. Intuitively, again, we can replace the t by theta, okay, because it's just a parameter that we're integrating with. And we have this very nice expression that says that intuitively this means that I can rotate this initial matrix, this initial rotation matrix, by some sort of angle theta around some sort of axis n hat. And if I do that, I'm going to reach a new rotation matrix, okay? Which is simply which is simply what I just said. What we're doing here is a parameterization of the rotation matrix. What does that mean? It means that if you give me any rotation matrix, I can find out the pair of n hat and theta. The n hat is a unit vector. Theta is just an angle between 0 to 360 or minus pi to pi. And they are called the exponential coordinates. If you take these two values together and you take the matrix exponential of them, you get a rotation matrix. Okay? This rotation matrix takes this old initial matrix and gives you a new one. Okay? You can think of it in this way.
For the vector n?
Yeah.
The vector, so why it's belongs to S?
Because it's a unit vector. It's not a vector of 3 numbers. It's 3 numbers that are constrained such that their magnitude is equal to 1, which is what we called before S2. If you remember, S1 was the x squared plus y squared is equal to 1. S3, S2 is equal to x squared plus y squared plus z squared is equal to 1. So it's a unit vector. Okay? So always unit vectors are not, they don't believe in R, they don't live in R3. They live in a manifold, which is the S2. So S2 here is the 2 sphere. Okay? So always unit vectors, they live in S2, in the sphere. They don't live in R3, even though there are 3 numbers. The exponential map now, so what we just defined here is a map that would take any Lie algebra element, as in SO3, small SO3, and will give us a rotation matrix, okay, given by this exponential matrix exponential map. You can show that it's surjective but not injective, okay? Just take it for granted without any proof, but again, you can see for yourself that any rotation matrix, there exists and some Lie algebra element, which means that there's some sort of axis that I can rotate around and reach this rotation matrix starting from any rotation matrix. Okay? So for example, if I give you this rotation matrix, okay, that this is the initial one and this is the final one, I can always find some axis that I can rotate around such that I reach this rotation matrix. So this is what surjectivity means. It means that I can reach all rotation matrices here. So there is no, so there doesn't exist any rotation matrix that I cannot represent by the exponential map. However, it's not injective, which means it's not 1-to-1, which means that there exists 2 axes that if I take the exponential coordinates, the exponential map with, I get the same rotation matrix. Okay, so I get the same rotation matrix even though n1 hat and n2 hat might be different. And here just a small remark on the notation. We're going to be calling, again, n hat, we introduced it so that we talk about unit vectors. We can take this n hat, which is 3 numbers, and put them in a skew-symmetric matrix form, right? This skew-symmetric matrix form, we're going to be call it n tilde. So we're not going to be calling it n hat tilde. Okay, it will be an ugly notation. So n tilde is simply the skew-symmetric matrix representation of the n hat. This is a unit vector, and this is its corresponding skew-symmetric matrix. Okay? Just as notation difference. Okay, this matrix exponential, we said, okay, it's like an infinite series expansion, okay, of I plus, again, there's the expression that we had before. But because of the fact that this is a skew-symmetric matrix, it has a very nice closed form solution. And this closed form solution is known as Rodriguez formula. Okay? Who here is familiar with this expression? Rodriguez formula? 1, 2, okay. So 3. Okay? So Rodriguez formula is an expression that simply is nothing else than this matrix, okay, this power series expansion, okay? But it will just use some properties of the skew-symmetric matrices such that we will not be needing to add or sum to infinity, okay? And we actually need to sum to infinity, but this summation to infinity will yield in the end the sine and the cosine, okay? The proof is 1 page, you can check it out for yourself. So no need to spend some time on it, but this is the expression of the matrix exponential. Okay. This is something that you can write in 1 line of Python code. It doesn't, there's no magic there. So the matrix exponential of the skew-symmetric matrix n tilde multiplied by theta, some angle, is equal to the identity plus sine theta multiplied by the skew-symmetric matrix n tilde plus 1 minus cosine theta multiplied by the square of the skew-symmetric matrix. The square of the skew-symmetric matrix, or like the square of any matrix, is what? A times A. So A squared is A multiplied by A. So this is what this expression means. And that's it. So this is something very nice. You can program very easily. You can have any axis, okay, and rotate around any angle, and you're going to get rotation matrix in this way. And vice versa. I can give you any rotation matrix, and you can represent it with some angle and some axis. So in the end, how many numbers? If I give you any rotation matrix, how many numbers can you represent with n hat and with theta? How many numbers in the end?
9.
If I give you 9 numbers, which is the rotation matrix, and then how many numbers do you need to represent n hat and theta? Only 3 numbers. Why?
Rotation around x, rotation around y, and x.
We never talked about this ugly way of describing rotations. Next slide. N hat has 3 numbers, but does it have 3 degrees of freedom? It's a unit vector. So if I give you 2 of them, the third one follows immediately, right? If I tell you, for example, the first 2 are 0, what is the third one? Has to be 1, right? If I tell you the first one is 1 over square root 2, and the second one is 0, what about the third one? Again, we can calculate. We should be 1 over square root 2, okay? Okay. So again, in this way, it makes sense, okay? So the n hat and the theta, so there are 3 numbers in the end. Okay, they are 4, but again, the first 3 are constrained to have a magnitude of 1. So this is a 3-number representation for a rotation matrix. Okay? You need theta. No, you need theta. So you mean if you multiply, okay, so you're saying that why don't we multiply n hat by theta and we get 3 numbers, and okay, this would work? Yeah, absolutely. This would be the same 3 numbers, but you're going to be lose the meaning of them, that one of them is an axis and another one is an angular velocity. If you do that, you're going to be losing this meaning, okay? Because they're going to be just 3 numbers, 1, 2, 3. Okay, but if you keep them in this separation, it will be very useful. And this is something we're going to be using for the joints later on. Okay, yeah.
We said 4, but we can
represent n by 2.
Yes.
The element is the angular velocity theta dot.
It's theta. No, if you're talking about a rotation matrix, then we represent it by theta. If you're talking about the angular velocity, you're presented by theta dot. So, okay. So the expression that we have here. So again, just as a recap. So if you give me theta dot and n hat, multiply them together, you get the angular velocity. If you give me theta and n hat, take the matrix exponential, you get a rotation matrix. That's it. Okay. Question?
The exponential function is injective. Exponential function is an injective.
Which one?
Exponential function, the mapping of the exponential function.
Yes, it's not injective.
Value for the exponential, I can have specific value. So
But the injectivity means that every element is unique. So every n hat maps to a unique R. Okay. This is what that means. This is what injectivity means, right? It's 1 to 1. This is not the case. I can give you two n's, two n hats that would map to the same R. Which means that what is this? What do these two lines imply? Exactly, that these three numbers do not uniquely represent the rotation matrix, right? Okay, so this is why it's not a good idea just to forget about rotation matrices and work with these three numbers. Can we do the same with quaternions? Again, instead of 3 numbers, 4 numbers, you're going to have the same problem. It will not be unique. Can we do it with Euler angles? How are actually Euler angles defined? Now we can introduce Euler angles in a very consistent way, or any other angles. If we rotate here about the original axes, okay, or the frame axes, or the coordinate frame axes, which in this case are x, y, and z. So I can rotate around this axis and this axis and this axis, or any other one. But these special ones, okay, will give me this minimalistic form of the rotation matrices. Okay, and you can prove it yourself. Okay, this will be part of the homework. So you can use this expression, okay, and substitute here the n hat to be 1, 0, 0, or 0, 1, 0, or 0, 0, 1. You can get these three expressions in the end. Okay, this notation is what the book uses. It uses this, again, it uses both the exponential of n hat and also the rotation, sorry, the exponential of n tilde, and the rotation about n hat and theta, and not rotation matrices. Okay, so they don't use the notation of R to represent this rotation, and they make a difference between what is rotation and what is orientation. Okay. So far we talked about orientation, which is this frame and this frame have different orientation relative to each other. But now we're talking about rotations, right? There's something action. There's an action that's going on. There's a discussion on that in the book. If you go and you find these two distinctions between rotation and orientation, this is what that means. Okay, so even though this is an element of SO3, we don't represent it by some R matrix, so that we explicitly say that this is a rotation around some axis by some angle. Now, how do you define again, Euler angles, if you wish, or the roll pitch yaw angles? Again, it's your call to choose 3 consecutive rotation matrices. Okay, 3 consecutive rotation matrices, 3 different angles, and you can get something like that. Again, are these unique? Of course not. Instead of having rotation by gamma around x hat and beta by around y hat and alpha around z hat, I can choose any. There are 12 other possibilities. Okay, and these 12 I can even do them in another way. I can have 22 different possibilities. Okay, it's a nightmare. Sorry, 24 possibilities. Okay, it will be a nightmare. Okay, these are called the 3-2-1 convention. There's a 1-2-3 convention. There's a 1-3-1-3, 2-1-2, and again. Of course, the most famous ones are the roll, pitch, and yaw. But again, is it unique to have 3 numbers here to represent this rotation matrix? The answer is no. Okay, this is just an aside. We're not going to be using it at any point. We used it. Okay, to be honest, we used it last lecture when we described the wrench axes, or when we describe multi-rotor aerial vehicles. But this is only for simplicity. Okay, for now we don't need them. Can we do the same from instead of SO3 to SE3? Because we talked about SO3 elements as being represented by some axis and some angle. Can we do the same for a 6-dimensional vector which corresponds to a twist? The answer is yes. So just like when we represented the angular velocity as the multiplication of n hat and theta dot, where n hat is a unit rotation axis and theta dot is a rotation rate, okay, some angular velocity around it. We can do the same for the twist. So the twist, we can represent it as the multiplication of some velocity, not angular velocity in general, some velocity, theta dot, and some screw axis, which is an R6. Multiply these two together, you're gonna get the 6-dimensional twist.
So what do you intend by the free velocity rate?
The what? V.
What does it free mean?
What is the what? V? The free? Theta dot? The free vector, this one.
They're not represented in the third frame.
No. If I said free vector, I don't know. It's not correct. No.
There is V against S expressed in nothing.
Expressed in nothing. Yeah, it's an abstract vector. Okay, we don't call this a free vector. Okay, if this was the axis that corresponds, for example, to rotation, we could call it a free vector, but we don't call it like that. Okay, it's not a free vector. It's just 6 numbers, okay, that are not represented. It's like a 6 vector, not represented yet in any frame. Yet, abstractly they make sense, which means that okay, I have this frame and this frame. This one is doing a relative motion compared to that one. How would you describe this relative motion as a function of time? By some sort of twist. Do you need to have numbers? No. For this abstract description, it makes sense. Just like when you say that I'm rotating around this axis without any numbers, it makes sense, right? The same here. So this can be represented in terms of what's known as a screw. Okay? So this is, again, an abstract idea, okay, an abstract concept, which is a screw, that we describe the twist in terms of that screw, just like when we described the angular velocity abstractly as some sort of rotation about some axis. Okay, so many hands, okay.
Whatever value you are getting, what's the exact?
You don't get numbers. You don't get numbers. Okay. If I say here this is an R6, it's after you express it in a frame. Again, the correct way of doing it, okay, which is I don't want to confuse you, or maybe I should have done it, is to add a new Euclidean space that doesn't have numbers. Okay.
Does not have numbers.
Does not have numbers. Yeah, it's just this. Where does this vector live? Where does this direction live? In some Euclidean space. This we introduced it at some point by the E, right? You remember the Euclidean space? It was just a collection of points, a collection of free vectors, didn't have numbers. When do you get numbers? After you put the frame, okay, and then you can talk about the numbers. Okay.
My question relates to this. The axis, like this, last time n was at least coincident with the two, or at least on the same part of rotation.
Yes.
But here, where the screw axis lies,
It's everywhere. It's again, it jumps around the place. At some point, it will reach infinity. If you have pure translation, it will reach infinity. This is the correct way of. This is the way of dealing with representing the screw. Again, in terms of representing the twist as as an actual screw, we're not going to be dealing with that. And okay, and there's a discussion for that in the book. We're going to be doing it in an easier way. So by looking at different cases, when we say we have rigid body motion, we're talking about two things, right? We're talking about rotation and translation, right? If we have a screw axis, it can have 3 conditions. It can have either a pure rotation, okay, which means that I have this frame, and this one is rotating with respect to that frame. Okay, so this is pure rotation. But you see now I'm not at the same point anymore. Okay, so even though I'm displaced, so there are two frames displaced from each other, but the motion itself is simply pure rotation. Okay. The other case is pure translation. Okay. Okay. This is pure translation, pure translation, pure translation. Okay. Displaced, then I have pure translation. The third one, which is Not needed in our applications, even though there are applications where you might have it as a screw motion. Okay, I'm doing a screw motion, which is translating and at the same time rotation about the same axis. This is known as a screw motion. These are the only three options that you have. Okay, so you can have either pure rotation, pure translation, or a screw motion. We're going to forget about the screw motion. We're going to be focusing only on the pure rotation and pure translation. Before you get lost, why are we doing that? Where did we start and where we are now? Is anyone still sharp enough to tell us? Absolutely, because we want to represent joints. So you can expect that the pure translation will be what? Which kind of joint? Prismatic joint. What about the pure rotation? A revolute joint. Okay, so don't lose focus. It will, again, your homework if you want. Okay, yeah, I'm not going to be doing it. For the pure translation, we have the following. The 6 numbers will have the following meaning. Okay, so these are 6 numbers, and we have a theta dot. The 6 numbers, so if you take a look, for example, in this example, so it will have zeros at the top, and the bottom 3 will correspond to this axis. And this axis is simply the translation axis. Okay, so for example, this is frame B, this is frame S, and this is the kind of motion I'm doing. Okay, so where is this axis? Point it. Where is the axis? It's this one, right? What are the numbers of it? No numbers yet. Right? I'm not talking about the numbers. Okay, so this is the axis around which the translation is happening, and the number theta dot. Okay, this number that when I multiply by this, I get a twist, is simply the linear velocity. Why don't we change the notation? Again, we can call it, for example, Q and Q dot, and everything would be nice. But again, just to stick with the book, okay? And this is, some books use Q and Q dot to represent prismatic and revolute joints. Some in this book they chose theta and theta dot to represent, again, which can mean angular displacement and also linear displacement. Okay? Depending on the context, it will make sense. So if I have a pure translation, then the first 3 numbers will be 0. The second 3 numbers will be the axis around which I have this translation, and the number theta dot will correspond to what is the speed I'm going along this axis. The second case, pure rotation, you might think it's easier. It's not. The pure rotation is, we have the first 3 numbers are the axis around which I'm doing the rotation, which makes sense, okay? Similar to what we had earlier. But the second 3 numbers is not easy. Okay, the way to think about it is that mathematics is very easy. Okay, and this is where we're gonna, when we solve examples, you're gonna find, okay, it's really a piece of cake. Getting your head around it needs some time to digest it. The mathematics says the following: the first 3 numbers are around the axis around which you're rotating. The second 3 numbers are minus the cross product between n hat and q, and minus n hat minus the cross product of n hat and q can be equivalently written as the cross product between q and n hat. Okay, we write it n hat and q for again for calculation purposes. Okay, but again, both are equivalent. What is the q? The q is simply any point on the axis. That's it. Any point on the axis. If I change the point, okay, so if I give you 2 q's and I ask you to calculate s, you're gonna get the same number. So any point on the axis doesn't change. Okay, and by the way, this axis goes from minus infinity to infinity. Okay, so along this huge axis, any point on it, q, would make this expression work. Okay.
What does it mean? I can understand the cross product between 2 vectors.
Yes.
So what does it mean? Cross product between vector and point.
This vector corresponds to rotation. Okay, and this vector corresponds to a position. This is something similar to tangential velocity, but in a 3D sense. You remember when you had when talking about tangential velocity, you have r cross omega, right? You remember r cross omega? To get tangential velocity, this is this expression. Okay. You definitely need some time to get your head around. Okay, don't try in this half an hour. The last, again, the theta dot here corresponds to an angular velocity. Okay, this is all what you need to know about the screw representation. Okay, it's just one way it looks when we have prismatic joints, okay, or pure translation, and another way when we have pure rotation. Okay, we're going to be seeing in a bit how does this, okay, in the end, okay, all fall together to talk about the forward kinematics. One last thing is yeah.
Q is represented as a point when calculated, means like a point coordinates according to this axis.
It's a point on the axis. You represent it in whatever frame that's up to you. It's a point even without talking about the coordinates. It's this point.
It's represented like
3 numbers. When you represent, for example, this screw axis into a frame B, then this will be NSB, NBS, and this will be QB. Okay. If you represent it in the S frame, this will be NBS. What did I say earlier? Well, you know what okay, the other way, okay? It's a point on the axis. Point on the axis, this point. So for example, if this is the axis, this point, this point, this point, all of them would work. Yes. Because this is a geometric axis. This is really, again, this has something to do with what's known as Chassel theory or Mozzi theory, that says that any rigid body rotation, any rigid body motion can be represented as a screw motion. Just like when we discussed, again, this makes much more sense because it's intuitive, you can visualize it. If I tell you any rotation matrix can be represented as rotation around some axis, it makes sense to everyone, right? This is its equivalent analogy. Okay? But instead of having a 3 vector, we have a 6 vector, that's it. Just like when we went from SO3 to SE3, everything became 3-dimensional, from 3-dimensional, 6-dimensional, exactly the same, okay? Intuitively, it's not easy, okay? Because again, you need to visualize screws, which is not easy at all, okay? But the math is very simple. Okay? And I'm gonna, again, if we make it to the examples, we're gonna be seeing, inshallah. In the same way, with analogy to what we did, H dot is equal to the twist until the 4 multiplied by H would have precisely another expression that looks like that. So H as a function of theta will be the exponential of this twist multiplied by the theta given the initial H matrix. So everything is exactly the same. The only thing we need to define now is this exponential. And again, using the Lie group structure, it's a map. It goes from SE3, which means it's a 4x4 matrix. The first 3, okay, 3x3 part is a SO3 element. It's a skew symmetric matrix, and the other 3 are like the linear part. And you have a matrix representation here. Okay, again, the matrix exponential. And again, you can expect it will have a closed form solution. I don't write it here, but again, you're going to be seeing it in the homework and in the book. Again, this matrix, again, the same way it's surjective. This map, sorry, exponential from the algebra to the group is also surjective, but not injective. Okay?
Sorry, Professor. The previous slide, I was on the question. Yeah, for this Q, if I'm expressing the SBS with a frame exactly along NB,
we're gonna have a lot of examples, okay, depending on the time. So again, it's much better to see it with the examples, which we're coming there. Okay, just wait. Okay. Now let's yeah.
Something like tangent spaces, because we go from
No. You go from a tangent space to the manifold. You don't go from the Lie group you go from the tangent space at some point to the algebra, which is a tangent space and a tangent space by a map. No. This exponential map actually is more general than just for Lie groups, but it has this very nice structure because of the Lie group. In general, manifolds also have this exponential map, okay? But again, and it's something that represents, okay, I'm going to stop, okay? Otherwise, some people might get lost. Now let's go to the products of the product of exponentials formula, and this will, okay, we'll take all of what we did and put it in, hopefully, in practice. Now let's see.
So are there any physical applications where we have combination of rotation and translation?
You mean the screw motion? Yeah, if you have a screw. So, for example, if you have like
But the robot itself is just only going down, or either only rotating.
but there are robots that have a screw. Okay, so there's a screw axis, there's a screw joint actually. You can make one. So just like it's called a screw. The screw itself is okay. You rotate it and it goes inside, right? If you have a screwdriver, what does a screwdriver do? You rotate, but it goes inside, right? What is this motion called? This is called a screw. You can also make a robot with that. You can make mechanisms with this construction. That's also possible. They're not famous, but it's doable. Okay. So now let's look at the products of exponential formula. Okay. What we're trying to do is the following. What we want to do is this. We want to calculate H4 with respect to 0. And we said that this is equal to 1 with respect to 0 as theta 1 multiplied by H2 with respect to 1 as theta 2. And H3 with respect to 2 as theta 3. And H4 as theta with respect to 3. Okay. Let's see. So this is the expression you're all familiar with. Now what we're saying is, okay, with what we just did, is that we can express the relative pose between any link I and the previous one, I minus 1, as a function of some angle by the matrix exponential, which I'm going to write like this, of the twist. And now we need to choose a frame. So the frame we're going to be choosing in, again, if you remember, maybe let me remind you of this expression that when we have I minus 1 dot, this is equal to the twist of multiplied by H I minus 1. Can anyone put the frames here? Again, I minus 1. But what about this one? The answer is I minus 1. Okay. So BS dot is equal to BS multiplied by BSS. Okay. We want to talk about the twist expressed in the previous frame. So this expression, again, it has this closed form solution. We're going to have here S I minus 1 multiplied by theta dot, so theta I, and we have here the homogeneous transformation of I minus 0 in the initial configuration. This makes sense to everyone? Yes. Sorry, okay, yeah, sorry. Thank you. I minus 1. Okay, makes sense? No, okay. It's 6 o'clock, so I minus 1. Yeah, makes sense. Okay. Here we assume also that Vi I minus 1 is equal to Si I minus 1 okay. I minus 1 multiplied by the theta I dot. Okay, so these are all of the expression that we have. Okay, for every link, we're going to be looking at some sort of screw that will represent the motion of this joint. Okay? The picture that we had was, again, just for your reminding that we had this frame, another frame, third frame, 1, 2, 3, and then we had here the fourth link. So this was this frame, frame. So this is 4, 3, 2, and here there was 1 and also 0 in the same place. Okay. What we're going to be doing is the following. We're going to be putting these expressions here for 1 with respect to 2, 2 with respect to 3, sorry, 1 with respect to 0, 2 with respect to 1, 3 with respect to 2. Okay. And we're going to be plugging it in there. Okay. Easy. So what we're going to having is the following. So H4. So H4 with respect to 0 is equal to the ES 1, 0, 0, theta 1 dot multiplied by H1, 0 of theta 1. So what I just did is replaced this term by this expression. And then I'm going to have multiplied by E S211 theta 2 dot H 210, sorry, theta yeah, okay. This one should be, this is not correct. This should be 0, yeah. This should be 0. Okay? And then I have, this is multiplied by E S322 theta 2 dot, no, theta 3 dot H 320 multiplied by in the end by H 430. Yeah, because it's just a constant. Yeah. Sorry? Theta. Yeah, thank you. This was a test for your concentration. Okay. And here it's correct. Okay. There's some nice property, okay? And the property is the following, that when we have the matrix exponential multiplied by before and after by homogeneous transformations, we can take these homogeneous transformations and put them in the exponential, okay? So again, this is just a sketch of it, but again, if you look at it in details, it will make sense. So if I take this matrix exponential, multiply it from the right and from the left, okay? Oh, sorry, from the left only, by hi minus 1 I, which is the inverse of that one, both of these would go inside of the exponential. So this is a matrix property. And you remember that the change, okay, wait a second, there's correction here. This should be S tilde everywhere. Okay, S tilde, S tilde, S tilde. Okay, so this is the matrix exponential of the S tilde. You remember that there was this coordinate transformation map that takes a twist in tilde form and would write it in another frame. Okay, does anyone remember that? If we have a twist in between any frame star and star, but expressed in, let's say, frame B, and then I have H SB and HBS. What is the resultant of this? This was equal to the V tilde star star in the S frame. Okay, you should have calculated this and proved it yourself in the assignment. So again, if we do this trick here, we'll be able to represent these. Okay, we're going to be changing where this twist is represented. Okay, so because this is again also a twist in tilde form, this is a twist in tilde form, and the same rule holds. So after doing all of these calculations and trying to clear it out, we're going to be getting a very, very neat formula, and the formula looks like this. This is the E of S tilde 1, 0, 0, theta 1, E multiplied by E S 2, 1, 0, tilde, theta 2, multiplied by E S3, 2, 0, tilde 4, multiplied by theta 3. multiplied by h for 0 at the 0. This is it. And if you have n links, okay, and n can be 100, you're going to have the same expression going from 1 0, 2 1, 3 2, 4 3, 5 4, and so on and so forth up till n minus 1. Let's understand first what this is, okay, and see what is this a big deal or not. What is this made? Theta. Theta, again. Again, how to memorize it easily. If you're talking about relative pose, then you have angles, theta. If you're talking about twist, you have theta dot. Okay, and this axis is the same in both cases. Okay, that's it. What? Here, this theta dot, okay, small dot here. Okay. But we didn't use this one at all. So this expression we didn't use. We're going to be using it next time, inshallah. But now we didn't use it at all. We only used this one and this one, which is the solution of it. We plugged it in here. We used this matrix, okay, of this property of the exponential, and we reached this expression. So this expression is very powerful. Okay? And this is nothing else than the forward kinematics map. Because this is a map that would take theta 1, theta 2, theta 3, and it will give you, in the end, a homogeneous transformation that corresponds to the end effector pose seen, okay, from the 0 frame. But what is these expressions here? Let's think about it for a second. What about this one? What is this term? The what? The pose of the end effector, okay,
Time 0.
with respect to the reference frame, to your stationary reference frame, at which scenario? At the initial condition, at your home configuration. The home configuration here is when you choose theta 1, theta 2, and theta 3 equal to 0. Okay. If we just draw it quickly, so again, for this example that we had, this is the scenario we're talking about. So link 1, link 2, link 3, and link 4. So 1, 2, 3, and 4. What? This is the home configuration. This is what the robot, when we say all of the joint angles are 0, this is where the robot is. We always have to define that, because you remember, this is exactly the same as choosing where the home in this room is, right? This is the home position of the robot. It has to go there. So this, we always know that. Okay. So this is the home configuration. What is the h of 4 with respect to 0? It's a pair of r4 with respect to 0 and psi of 4 with respect to 0. What is r4 with respect to 0? Identity in 3 dimensions. It's a 3 by 3 matrix, identity, because I chose, and again, this is a choice, we chose that the reference frame here is identical to the 1 frame. So this is the 0 frame, and you see here, they have the same orientation. I'm doing it by inspection. What about the psi of 4 with respect to 0? It is 3 numbers. It's in this direction, L1 plus L2 plus L3. So it's L1 plus L2 plus L3, and I have 0 and 0. Clear? Let's go back. Because it's in 3D. We're going to be working everything with 3D because we're talking about homogeneous transformation in SE3. Okay. What?
320 is it?
Correct. 320. What is now this 32? What is this axis 32, axis 21, axis 10? Let's go to this picture. So this robot, the joints that we have, the first joint is what kind of joint? is what kind of joint? It's a revolute joint, right? Around which axis is it rotating? Around this axis. So this is theta 1. And this joint is rotating around this axis, theta 2. And this joint is rotating around this axis, theta 3. Okay. Now let's do the following exercise. Let's see. What we need to do now is write S of 1 with respect to 0. 1 with respect to 0 expressed in the 0 frame. Okay. And we said that if it's a revolute joint, then it will have a form that looks like this. N hat here and minus N hat cross product with some Q. Okay. Everything will be expressed in the 0 frame. And we're talking about a particular axis. It's the one that we draw like this. This is the axis we're talking about, okay? Because it describes the relative motion between link 1 and link 0. So what is this axis N0 as seen from the N hat as seen from the 0 frame? N hat as seen from the 0 frame. What is it? 0, 0, 1. Why are you saying that? I'm rotating around the z-axis. If I assume that this is 0, this is 1, this is x, and this is y, and this is z, so I'm rotating in positive z-axis. What about the q? For this axis, it's 0. Why is that? Because the origin of frame S is along the axis, and whenever you have that, this means that I can choose any point here. What is the best point to choose here to make our life easier? Choose the origin, which is along this axis. So I have 0, 0, 0. So what is in the end, this expression is 0, 0, 1, 0, 0, 0. Another example.
R40, here is
I3.
I because
Identity.
why R40 is I in this position only?
In this position only. So, okay, that's good point. So we're talking here about in the 0 configuration, in the home configuration. Yeah. If you choose the point Q, for example, this point or that point or this point, yes, you're going to get the same number. Okay, because you're going to be taking the cross product with 0, 0, 1, and it will disappear. So the cross product with 0, 0, 1 along the z-axis will always be 0. Okay. Let's look at S2 with respect to 1 expressed in the 0 frame. So what does it look like? It looks like this because it's also a revolute joint. So it's some n hat expressed in the 0 frame and another n hat cross with the q0. Again, these are different n's and n hats and q's. To be proper, you have to define it like this. So I have to say that this is S100. So this should be n hat 100. This should be q100 and so on. Okay. So, but again, the way to do it is actually do it in a table. Okay. You're gonna have a lot of practice to do it, but this is just to complete this part. So the n hat 0, what is the axis? Z-axis. Okay. I'm also rotating around the z-axis. Expressed in this frame, it's also 0, 0, 1. Okay. So n hat 0 also in this case is 0, 0, 1. What about the q0 for this example, for this axis? It's L1 in this direction and 0, 0 because I'm not going up and I'm not going to the front. So it's L1, 0, 0, L1, 0, 0. Take the cross product of 0, 0, 1 with L1, 0, 0. Okay, this is not a good way. L1, 0, 0. You're going to get the second term of what you should go here. So this should be 0, 0, 1. And what should go in there will be 0, 0 minus L1. Sorry. 0, 0 minus L1. Okay, so this is the second part. Let's take the third. Oops. Okay, let's take S 3, 2, 0, which is again n hat 0 and minus n hat 0 cross with Q0. What about the n hat 0? It's also 0, 0, 1 because I'm also rotating around the same axis. What about the Q0? It's L1 plus L2, 0, 0, which means in the end, this will be 0, 0, 1, 0, 0 minus L1 minus L. 1 second. Yeah, of course, yeah. Minus L1 minus L2. And that's it. Take these numbers. Again, we're talking about numbers here. Okay, we're talking about numbers, something you can easily program. If you have this robot, you can do it by inspection. We only drew one drawing. We looked at the robot in this home configuration. We take all of these numbers, plugging them in this expression, which is something you can do put on the computer. You're going to be working with that, okay, inshallah. You're going to put this on the computer, and in the end, you're going to get a huge homogeneous matrix transformation that will map. You give it 3 angles, and it will give you a homogeneous transformation that corresponds to the location of this and the angle of it in the 0 frame. Yeah.
You just simply combine the exponentials into one exponential?
No, because this is the whole idea of why we're doing this. Because we're looking only at the relative, okay? Because these are a function of theta 1, theta 2, and theta 3. You cannot combine them to something that...
S1, 0, 0, theta 1 plus S2.
No, you cannot do that, no.
Exponential property.
I don't think it will work. No, I don't think it will work. There's also another benefit of doing this. What if you're interested in the location of this frame with respect to the 0? So we're talking only here about the end effector frame. If I want to do the same expression, but looking at H3 with respect to 0 as a function of theta 1 and theta 2, how to calculate that? H3, 0 at the 0, okay, home position, multiplied by which one it will be? 3 to 0, then I'm going to have, first of all, 3 to 0 and 4 to 0, again, there's just an offset. So from 3 to 4 is just a constant matrix. What's more interesting is the 2, 1. So going from the 2, then I'm going to have, this one will drop out, okay? So I'm going to have H2, 0 multiplied by 2, 1, 0, and 1, 0, 0, everything with this part will be the same. If I want to have 1, 0, H1, 0 as a function of theta 1 and theta 2 and theta 3. Again, forget about these two, multiply H1 of 0 by this one, and it's very net. Okay. So you can do it, you can get all points you're interested in. If you have now extra points in between, for example, if we have center of mass frames, we're going to be doing for the dynamics part, you can easily add frames, and try to figure out, okay, what should be multiplied in this way, and it's a piece of cake. Okay, we have to stop. Okay, if you have any questions, I can take them after the recording for people who want to leave. Okay.